Let's talk about the properties of a stationary AR1. And our AR1 is defined to be xt equals delta, which I'm calling a constant, plus phi1 xt minus 1 plus at, noting that ATs are normally distributed mean zero with variance sigma squared A, paying close attention to that subscript of A, meaning again that that's the variance of the ATs. Okay, so the first property I'd like to show is we know that expected value of xt equals mu, but I'd like to show that that equals, under this parameterization, delta over 1 minus phi1. That the mean, that constant mean is, when the model can be written like this, is that delta divided by 1 minus phi1. So how are we going to do that? We're going to say, all right, we've got the expected value of xt, great, equals, and we'll call that the expected value of delta plus phi1 xt minus 1 plus at. That looks great. Equals, and we can say that that is the expected value of delta plus the expected value of phi1 xt minus 1 plus the expected value of at. Okay, and that equals delta plus phi1, just because the expected value of a constant is just the constant, plus phi1 can come outside because it's a constant, expected value of xt minus 1 plus, now the expected value of at is normally distributed with mean zero, so the expected value of at is just 0. So I can rewrite this as delta plus phi1, and since xt is stationary, since this is a stationary process, the expected value of xt minus 1 is the same as the expected value of xt, and so that is simply mu plus 0. And so now here we have mu, because the expected value of xt is mu, equals delta plus phi1 mu, which, just a little bit of algebra takes us to mu, take that over here, minus phi1 mu1, or sorry, phi1, don't get your ones mixed up, so phi1 mu equals delta. And so then that will be mu times 1 minus phi1 equals delta, just factoring out the mu. And that will lead us to mu equaling delta divided by 1 minus phi1 for a stationary AR1. That's the one. Okay, great. So that's the first property. Stay tuned for the next property. So let's talk about another property of a stationary AR1, noting that we're going to keep with xt equals delta, which is a constant, plus phi1 xt minus 1 plus at for our AR1, where the ATs are normally distributed with mean 0 and variance sigma squared sub a. So what we're going to do for simplicity in this one is assume that mu equals 0. And in our last property, we saw that mu equaled delta over 1 minus phi1. So that's what we showed from the last property that we had. And so if mu equals 0, then this implies delta equals 0. So we will have xt equals phi1 xt minus 1 plus at if we're in this zero mean form, where again we'll just, for completeness, say we have that. Okay, fantastic. So since we're in the zero mean form, we're just going to, again, for simplicity, assume that we have zero mean, and we want to show that we're going to say sigma squared x, which equals the expected value of xt squared in this case, is equal to sigma squared A, the variance of the white noise, divided by 1 minus phi1 squared. We'd like to show that. So let's go ahead and get started on it. We're going to say that the expected value, noting that this is the variance of the x's, sigma squared x. So the expected value of xt squared equals the expected value by substitution of phi1 right here, phi1 xt minus 1 plus at, and that whole thing squared. And then we'll FOIL that out, so that'll be the expected value of, and that will be phi1 squared xt minus 1 squared, right? And it'll be plus 2 xt minus 1 at plus at squared. Expected value of that. The expected value of the sum is the sum of the expected values. So this will be equal to the expected value of phi1 squared xt minus 1 squared plus 2, I'll just say plus the expected value of 2 xt minus 1 at, and plus the expected value of at squared. And we'll do some more simplification here. That is phi1 squared expected value of xt minus 1 squared plus 2 times the expected value of xt minus 1 at plus the expected value of at squared. All right, so we squeezed that in there, but let's keep rocking it. So this is phi1 squared, and we have the expected value of xt minus 1 squared. But since xt minus 1 is coming from the same process as xt, we know that's a stationary process, that the variance, right, that we know that it has constant variance over time. So the variance of xt minus 1 is the same as the variance of xt. So that will just be sigma squared. So I've got phi1 squared sigma squared plus, and this is 2 times, now xt minus 1 and at, the observation is assumed to be independent of its noise. So this would be, when you've got two variables that are independent, we know that that is the expected value of xt minus 1 times the expected value of at. And we know that plus, that's the expected value of at squared, where we know that the at's have zero mean, and so the expected value of at squared is just the variance of at squared, and the variance of at squared is sigma squared a. So this is just sigma squared a. All right, so we're almost there. So all we need to note here is that the expected value of at is, of course, 0. So this will go to 0, and that whole term will go to 0. So that is equal to phi1 squared times sigma squared plus sigma squared. Sorry, these should be that sigma squared x. We got to keep that noted, right? Sigma squared x, because that's the variance. This here is the variance of the x's. So that's sigma squared x. That goes to 0. That's sigma squared a. So that's sigma squared x plus sigma squared a. And all of that equals, that's sigma squared x. So that's just sigma squared x. So then finally we have sigma squared x. So we'll write that down here. Sigma squared x equals this, phi1 squared sigma squared x plus sigma squared a. And so then I'll get these, I'll put all of the sigma squared x's on one side. So that's sigma squared x minus phi1 squared sigma squared x equals sigma squared a. And of course, we've got two more steps here. That's going to imply, if I factor out a sigma squared x, that's sigma squared x 1 minus phi1 squared equals sigma squared a. So I have sigma squared x times 1 minus phi1 squared equals sigma squared a. And so we will write our final result right here, which is that sigma squared x equals sigma squared a divided by 1 minus phi1 squared. 1 minus phi1 squared. Which, note, of course, does not depend on time. It's a stationary time series. And now we have a property, an identity there for how to calculate sigma squared x given the model. So great job. There's another property of a stationary AR1.